When astronomers say a huge rotating structure made of galaxies and dark matter has been detected, they are not describing a single object spinning like a wheel in space. They are talking about something far larger, subtler, and more unsettling. A pattern. A coherent motion spread across vast cosmic distances, involving thousands of galaxies and an even greater amount of invisible matter, all appearing to participate in a shared rotational behavior. This is not supposed to be easy to see, and it is not supposed to be common, which is exactly why the detection matters. On the largest scales, the universe is expected to be statistically uniform. Galaxies cluster into filaments and walls, separated by enormous voids, forming what is often called the cosmic web. Within that web, local motions are expected. Galaxies orbit within clusters. Clusters fall toward each other. Matter flows along filaments under gravity. But over truly immense scales, these motions should average out. There should be no preferred direction, no giant spin, no sense that the universe, or parts of it, have a built-in rotation. The newly detected structure challenges that expectation, not by overturning cosmology outright, but by adding tension where simplicity once lived. The detection itself does not come from watching galaxies visibly whirl around a center. The timescales are far too long for that. Instead, astronomers infer rotation statistically by measuring systematic velocity differences across enormous regions of space. When galaxies on one side of a structure consistently move toward us while galaxies on the opposite side move away, that pattern can indicate rotation, not of individual galaxies, but of the entire large-scale structure they inhabit. What makes this particularly striking is the scale involved. We are not talking about a single galaxy cluster. We are not even talking about a supercluster in the traditional sense. The structure spans hundreds of millions, possibly billions, of light years. At that scale, gravity still rules, but its effects are usually messy and directional rather than organized. Seeing a coherent rotational signal across such distances suggests that something in the early universe set this motion in place and that it has persisted ever since. Dark matter plays a central role here. Most of the mass involved in these structures is not visible. Galaxies are just tracers, bright markers floating in a much larger, darker gravitational landscape. When astronomers detect rotation on these scales, they are really detecting the motion of dark matter itself, inferred through how galaxies move within its gravitational pull. This is important because dark matter is expected to be cold, collisionless, and largely passive. It clumps under gravity, but it does not interact in ways that easily produce large-scale rotation. Local angular momentum is common. Galaxies spin, halos spin, but coherent angular momentum extending across cosmic filaments is much harder to explain. One possible explanation lies in the conditions of the early universe. Shortly after the Big Bang, matter was not evenly distributed. Tiny fluctuations in density were present everywhere. Over time, gravity amplified those fluctuations, drawing matter into filaments and nodes. If some regions had slightly asymmetric initial conditions, they could have acquired angular momentum as they collapsed. That momentum, once established, would be conserved. On small scales, this process explains why galaxies rotate. On larger scales, it becomes more speculative, but not impossible. Another contributing factor could be cosmic flows. Matter does not simply fall straight into gravitational wells. It streams along filaments, sometimes merging at angles rather than head-on. Over billions of years, these flows can imprint rotational patterns on the structures they feed. The key question is whether such processes can produce rotation that remains coherent over the enormous scales now being reported. What makes the detection credible is that it does not rely on a single measurement or a single line of sight. It emerges from large surveys of galaxy redshifts, positions, and velocities. These surveys map the three-dimensional structure of the universe with increasing precision. When patterns appear independently across different datasets and analysis methods, they demand attention. Still, astronomers are cautious. Large-scale signals are notoriously difficult to interpret. Selection effects, survey geometry, and observational biases can all produce apparent patterns that vanish under closer scrutiny. This is why claims like this are framed carefully. The language is statistical, probabilistic, and restrained. No one is claiming the universe is spinning like a top. They are saying that within a specific, massive structure, rotation appears to be present at a level that exceeds random expectation. If confirmed, the implications are subtle but profound. It would suggest that angular momentum can be correlated across far larger scales than previously assumed. That would influence how we model structure formation, especially in simulations that currently assume such correlations decay quickly with distance. It could also affect how we interpret cosmic anisotropies, the slight directional differences we observe in large-scale measurements. Importantly, this does not violate known physics. General relativity allows for rotating solutions. The early universe could, in principle, seed large-scale angular momentum without breaking fundamental laws. The challenge is not possibility, but probability. How likely is it that such a structure would form under standard cosmological assumptions? That is where theory and observation now meet. There is also a temptation to overinterpret. Whenever large, rotating structures are mentioned, ideas about a rotating universe or preferred cosmic directions quickly surface. These ideas are not new, and they have been tested repeatedly. So far, the universe appears isotropic on the largest scales we can measure. A single rotating structure, no matter how large, does not overturn that conclusion. It adds texture, not revolution. Dark matter's involvement is especially intriguing because it cannot be observed directly. Its motion is inferred through gravity alone. Detecting rotation in dark matter on these scales provides a rare constraint on its behavior. It reinforces the idea that dark matter is not just a static backdrop, but an active participant in the universe's dynamical history. There is also a practical aspect to this discovery. Large-scale rotation can influence how galaxies form and evolve within these structures. Angular momentum affects gas accretion, star formation rates, and merger histories. If galaxies inherit some of their spin from the larger environment they live in, that connection could explain correlations that have long puzzled astronomers. As data improves, this picture will sharpen. Upcoming surveys will map even larger volumes of space with better precision. They will either confirm the presence of similar rotating structures elsewhere or show that this one is a rare outlier. Both outcomes are informative. A common phenomenon reshapes theory. A rare one challenges simulations to explain exceptional cases. What is striking is how quiet the discovery is compared to its scale. There are no dramatic images of spinning galaxy rings. No single frame captures the motion. The evidence lives in numbers, trends, and careful statistical analysis. This is how modern cosmology works. The universe reveals itself not through spectacle, but through persistence. In the end, the detection of a huge rotating structure of galaxies and dark matter does not tell us that the universe is broken or that our models are wrong. It tells us that the universe is richer than our simplified descriptions. Gravity, acting over immense times and distances, can organize matter in ways that still surprise us.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.